Hello everyone, I'm Tiago Perez. I'm a PG student at TalTech under supervision of the Samuel Paglini, and today I'm talking about hardware Trojans and my presentation is titled A Novel Site Trojan Insertion via SEO. This is the content of my presentation. I'll give a very briefly overview here. Then I will talk more about how we design the Trojan. Then I talk how we insert the Trojan. Then I'll show some experiments and results. Then talk a little about the test sheet that we are planning and my conclusion. The main goal of this work is to perform a sidechain attack by paralysis assisted by this hard Trojan that we are designing, and we want to leak multiple bits per signature reading. So the motivation of this is to perform those type of attacks much faster, processing much less data. And the challenge here is to design and search the Trojan. The novelty of this work is how we insert the Trojan. We are utilizing the engineering changing order. That's a feature available in almost all IDEA tools, and it's used for saving time in the final steps of the design, for making small fix and not changing the entire design, and you don't have to redo all the flow. So this is your typical integral secret design process, from the RTL to the GDS here, then manufacturing, assembling, testing, package, and to the end user. As said here today, the design components outsource the manufacturing for many reasons. One is it's too expensive to own a foundry and a high-end foundry, and today to reach the high-end technology, you have to outsource the manufacturing. So this leads to a potential threat that a hog element inside the foundry can manipulate your GDS, and this is often called the fabrication time attack. In this work or threat model, we assume that this hog element, this attacker, has access to all technology and cell libraries from that you utilize for your design, and also this attacker has expertise in circuit design and can recognize at least the target, only assessing the GDS2. So we are here designing hardware Trojans. A hardware Trojan has mainly two components, a trigger and a payload. The trigger is which turn on the Trojan, and the payload is what the Trojan do. In this work, our Trojan target crypto cores that we are intending to leak the crypto key. Our trigger is some kind of signal that tells us the processing of the crypto core stopped, so he's going idle, and our payload is to induce extra power consumption in a controlled manner. So these are the aspects of our hardware Trojan. And if you go back to that graph there, you can easily see that our hardware Trojan has a digital trigger, it's sequential, as the clock is synchronous, and our payload is digital and derived nodes. So this is the flow of insertion of the hardware Trojan, and this is our architecture. Our Trojan has two main blocks here. The Trojan controller that's responsible to connect the target signals to the ring oscillator that we want to leak, and to trigger the ring oscillator. The ring oscillator is a special architecture that generates a oscillating signal, and the frequency of this signal can be changing by changing the path delay on its ring. So we can create, we can tie specific frequency to each of the bits configuration that you want to leak. In this example here, we can leak 2 bits at a time, and this architecture can be scaled up to more bits or scaled down to a single bit. This clock divider here is required when the system clock is too fast and provokes the time violations inside the Trojan controller. This is how the example of the functionality of your hardware Trojan. Enable is our trigger signal. S0 and S1 are the leaking bits, and our output is the oscillating signal of output of the ring oscillator. As you can see, when the Trojan, when the signal enable is asserted, our Trojan start to work, and the power consumption is increased. And if we measure this only, we can see that the bits that are connected to the Trojan controller are 00 and forward on. So for inserting the Trojan, first of all, we only have access to the GDS2, so we have to extract the net list. And this can be done utilizing any CAD tools, example here, the Cadence Virtuoso. Then we have to estimate the operating frequency of the target. So this can be done by performing time analysis. First, you have to guess a frequency value, perform a time analysis, and observe the critical path. If this lags to negative, you have to relax your frequency, and if it's too positive, you have to increase your frequency until you achieve a time slack near 0, and you have a good estimation of frequency. Then with the net list and your timing constraints, you can perform a straightforward power analysis, so we can design your Trojan. And with the information I said before, you can design the Trojan. With the operating value, you can assess if the Trojan works with that value, and so on. And here's the trick part. We are inserting the Trojan utilizing the ECO flow, and this is very simple. You only have to modify your extract net list, inserting the Trojan as a module. And then, for example, here I'm using the Innovus, and it's only one command. You have to give as an input the original database and your modified net list here. And what did the ECO do? The ECO changed the empty space that are potential fillers and put the Trojan there. And doing this, the target placement is not changing. It's untouched. Same as the routing, but the routing is difficult to show graphically, and I'm here only showing the placement. For our experimental investigation, utilize 2 crypto cores, the AES for its popularity and the present for its novelty in lightweight. To show the capabilities of the ECO, we implement those 2 cores, modifying these parameters here, the frequency of operational frequency and the density of the implementation. We start with a very low frequency, very low density, until the high frequency and the high density. These are the standalone implementations results. As you can see, the density doesn't change much the power consumption, and for modeling our Trojan, we utilize the leakage plus the clock tree power and some design margin, so you can design the Trojan to be more or less stealth as you want. As I said before, the density doesn't change much, so you have to only design for ring oscillators regarding the frequency of the target. And here highlighting, I'm showing you a ring oscillator with 6 delay cells and 10 inverters, and the frequencies goes and the power consumptions increases goes to 20 microwatts to 13 here. These are the physical characteristics of each hardware Trojan. For the high frequency, I have to include the clock divider. That's why for the high frequency, there's more hashtags here. This figure shows how the density changes after you insert the hardware Trojan. As you can see, before the Trojan, the design was very dense, and after you can check some areas with 100% of utilization. And this means that even though the target is very dense, you can insert a Trojan that's not that smaller, that not small in that target. And also we have to check the performance of the target after this hard Trojan, even though we are not putting logic directly on the target. The routing wires and the extra cylinder cells that we are placing there introduce couple capacities, and it impacted the performance of the target. So here I'm showing the example for the fastest ones, and for the ES the impact was not that great, and the PST the impact was higher, but not enough to violate our safety margin here that we're putting more or less 20 picoseconds. So from these census, we can see that the ECO didn't impacted negatively the time performance of the target. We are planning a test chip, and we are implementing the 4 crypto cores and a block to control that. In this test chip, I introduce 5 power domains, so we can turn on and turn off individually each crypto core for more precisely measurement of the power, and only 2 clock domains, because I'm turning on only one at a time. So we don't need 4 clock domains for the crypto cores. Here is the floor plan of our test chip, and you can see more or less the size of the implementations, that the AES with 1 gigahertz is very, very big compared with the PST present with a very slow frequency. This test chip has 1 square millimeter of area. We utilize a 65 nanometer commercial technology, and we are expecting to receive the parts in June. And this is a review here. In conclusion, we show that the ECO flow can be used for malicious user other than the original purpose of the feature. A hog element has all the means to utilize this flow and introduce all kinds of modifications into a design, only assessing the GDS2. And that was my presentation, and I'm prepared for your questions if you have any.